Hello everyone, my name is Sheikh Dobir Hossain. I am from the University of Texas at El Paso, USA. And today in this IEEE Flaps 2022 conference, I am going to represent one of my research work on flexible chipless RFID temperature memory sensor. So I want to start off my presentation with a short introduction on why, where, and how the sensing elements and object tracking systems are important. So we all know barcode. So barcode are very popular in object tracking systems because of its low cost and easy of fabrication. However, the use of barcode is labor intensive. It is because it requires to scan the object directly or object individually and direct line of sights. That's why it's labor intensive. On the other hand, the chip-based RFID tag can avoid all those complexities of the barcode, but the presence of the chip on the tag makes it costly and fabrication much difficulties. So currently the chipless RFID tag are very popular because it's low cost and easy of fabrication. Also, the introduction of some sensing elements with this tag, making such device very promising. Some application like, for example, to save the perishable products such as milk or meat or canned food or like ice cream, we need to monitor some environmental parameters like temperature or moisture. If the threshold value of those parameters gets crossed, then this kind of products maybe get spoiled or decay or become unsafe to consume. That's why in such application, such kind of devices are very promising that really help us to avoid the waste and loss of the products. So in this research, we fabricated an RFID temperature memory sensor where we introduced some smart sensing material that really help us to detect the temperature threshold and also store the information, the temperature crossing event information permanently. So now I'm gonna let you know what motivated me to do this research. So the production of an efficient chipless RFID tag to replace the barcode is still in research stage due to the challenges of cost, data density, and data capacity within the desired dimension with the flexible properties. Also, it is really difficult to implement in real world environment. However, the idea of the chipless RFID tag has attained a lot of attention of the research community because of its some cool properties, like the introduction of some extra feature like the 3D printability, the ability of sensing multiple parameters such as temperature, moisture, pressure, and the storing those information permanently without using any external memory makes such kind of RFID tag sensor unique compared to the traditional sensor or the barcode. So however, to achieve all these properties using a sensor is really difficult and is still in research stage. So in this research, my objective is to design a flexible chipless RFID temperature memory sensor, and we wanna introduce some smart material on that sensor to detect some physical parameters and store those information permanently. And also we use the additive manufacturing technology to fabricate our sensor. So it makes the fabrication process much easier compared to some other traditional process, and also makes also reduce the cost of the sensor as well. So as I said, like my aim was to create a flexible chipless RFID temperature memory sensor. So to get all those properties, I used 4 different materials over here. So I chose PDMS because it has low Young modulus, which means I use this PDMS to create the substrate of the device. So I chose this one because it has low Young modulus, which means it provides better flexibility. Also, it has some other cool properties like thermal stability, and within the same thickness, we can tune the permittivity only by changing the mixing ratio of PDMS and the curing agent. Also, it's very simple to prepare. And then I I also chose the ethectic gallium indium as a liquid metal. I inject this metal inside the microchannel to get the resonator. So I choose this metal to get a sensor because it has low melting point. So even at room temperature, it works as a liquid metal. So it also helps us to get to achieve the flexible device. And then we chose two different oils like grapeseed oil and coconut oil, and we mixed them together to get a wax of different melting point, and we use that wax to coat the microchannel to achieve the desired temperature threshold detection. So here's the design or geometry of our fabricated sensor. So our fabricated sensor has three different layers that has been shown in the top left picture. So it has substrate layer, microchannels layer, and the film layer. The substrate layer is made with PDMS, where the microchannel layers is been made with the liquid metal, and we added a top layer, film layer on top of this channel to avoid the leakage of the liquid metal. And we also coated this microchannel using the oil solution that we prepared earlier, that really help us to detect the temperature thresholds. So, and the bottom left picture shows the dimension layout of our sensor. The substrate is like an square shape with a length of 23.5 millimeter. Thickness is 1 millimeter, and the depth of the channel is 0.8 millimeter. And the radius of the different channels and the width of the channels and the gap between the channels also mentioned in the given picture. We also calculated the resonant frequencies of our sensor using the given equations, and we found that the resonant frequency of the sensor mainly depends on the total inductance and the capacitance of the resonator. So this slide will help us to understand how a sensor works. So here the transmitting antenna sends an ultra wideband signals toward the sensor, and the information of the sensor gets encoded with the ultra wideband signal and backscattered toward the receiving antenna, and thus we get true resonance frequency peak. And the bottom two picture will help us how we get this true resonance frequency peak out of 3 resonator. So we found that at lower resonance frequency, the current density becomes maximum at the outer 2 rings, and for the higher resonant frequency, the induced current becomes maximum at the inner 2 rings. So, in this way, we get 2 different resonance frequency peak. And then when the environmental temperature gets melted, the coated oil gets, that means when the environmental temperature crosses the threshold value, then the oil inside the channel gets melted, which means the effective length of the channel gets increased, because this part is contains some liquid metal over here, and over this one is the liquid oil. So when the oil gets melted, then the overall length get increased. So that's why the resonance frequency gets shifted once the environmental temperature crosses threshold value. So as the fabrication process that we have followed to fabricate our sensor in our lab, so it basically have 4 different steps. So in the first steps, we model microchannel-based molds on on-shape CAD on-shape, and we fabricated that molds using a 3D printer. And then in the second steps, we transfer this channel onto the PDMS substrate. And in these steps, we pour PDMS inside the molds, and after degassing and curing it, we get our desired microchannel-based PDMS substrate. And in the third steps, we coated the microchannels with the oil mixture that we prepared earlier. And in the final steps, we added the film layer on top of the channels, and then we inject the liquid metal inside the channels. And finally, we get our prototype, and that is given in the bottom left picture, where the left one is the top view and the right one is the side view, and the dimension is comparable with the US $2. So then we tested tested the performance of our sensor. So that we tested it using a field flux RF analyzer, and the change of reflection coefficient and resonance frequency at different temperature plot is shown over, on top right picture, and the results have been summarized in the table below. And from that, if we look over the table below, then it explains that like when the temperature is just below, that means when the environmental temperature is just below less than 4 degrees, then our resonator shows two different resonance peaks, which are 4.95 gigahertz and 6.10 gigahertz, and the SNN parameters around 20 dB. Then we increase the temperature from 4 degree to less than 8 degree, and we found that the first resonance frequency gets shifted to 4.50 gigahertz, and at the same time, NN parameters reduced to minus 6.74, while the other resonance frequency and SNN parameter remains same. Then we increase the temperature to 8 degree, and we found that the first resonance frequency and SNN parameter remains same once it gets shifted, while the other one, the resonance frequency gets shifted to 5.96 gigahertz, and at the same time, SNN parameter reduced to minus 6.80 dB. Then again, we increase the temperature beyond the 8 degree, and we found that once the resonance frequency gets shifted, in both cases, there are no further change of the resonance frequency. That means the resonance frequency shift is permanent over there. So thus we can conclude that our sensor can detect two different temperature like 4 degree and 8 degree only through changing the resonance frequency. So here is the flexibility and memory effect verification of our sensor. So the flexibility verification has been explained using this plot, and we found that with the different bending angles, both the SNN parameters and resonance frequency gets shifted towards the lower value, and we got some visible range of these parameters up to 52 degree bending angle, and the bending angle has been measured over a cylindrical body, and we found that when we cross the bending angle beyond the 52 degree, then there is no such visible value of these two parameters. So from this discussion, we can say like our sensor can work up to 52 degree bending angle. That means it has some flexible properties. And also we tried to verify the memory effect, and that has been explained using these two pictures. So from the bottom two picture, it's explained that like when the temperature is just below 4 degree, then our sensor shows two different resonance frequencies, which are 6.1 gigahertz and 4.95 gigahertz. Then we change the temperature, environmental temperature, just above the 4 degree, but below the 8 degree. And we found that the resonance frequency for this one gets shifted to 4.96 to 4.56, while the other one remains same. Then we increase the temperature again above the 8 degree, and we found that the resonance frequency for the left one gets shifted to 6.1 to 5.96 gigahertz. And if we further increase the heat or the cool it above or below the threshold temperature, then we found that the resonance frequency shift is permanent. That means from this we can say that once the resonance frequency gets shifted because of crossing of the threshold temperature, even if we increase or decrease the temperature, the resonance frequency shift, there is no further resonance frequency shift. It means it can store the temperature threshold events permanently. So thus it can store the information without using any external memory. So let me show you a literature review of similar work and a comparison with our fabricated sensor. So the author of work 4 have created a sensor with using a 3D printer, and it shows that the flexibility properties, but it doesn't have the ability to store the information. On the other hand, the work of work 5 and 6 can store the information permanently, but the problem is they are very big in size. And we found that the work 7 is very much close to our works in terms of dimension or temperature threshold detection, and both can store the information permanently. But the author 7 used the chemical etching process to fabricate the sensor, and this sensor do not have the deformation capability, but our sensors have been fabricated using PDMS and using additive manufacturing technology. That's why it have the flexible properties. So from this analysis, like we can say our work can be a significant extension of this literature, and it might be suitable for some cold chain applications. So for the conclusion in this research, we have fabricated and tested a microchannel-based Chipless RFID tag sensor, and we created the microchannels using the 3D printed molds that makes the fabrication much easier. And the fabricated sensor is able to detect two different temperature thresholds, which are 4 degree and 8 degree. And this sensor even can detect this temperature even up to 52 degree bending angle. Also, it can store the temperature events permanently without using any external memory. So it means it reduces the sensor cost and eliminate the need for constant signal monitoring. And in future, so what we're gonna do, like in this work, we have just looked at 2 oil mixing ratios, but in future, we wanna investigate the impact of various oil ratios and also wanna explore how to use this tag to sense multiple parameters like temperature, moisture, pressure, etc., instead of just a single temperature parameters. So as a reference that we have used during our research. So if you are interested, then you can go through this, and that's all. Thank you so much for watching these presentations, and welcome you all at the University of Texas at El Paso, USA. And if you have any question, please feel free to ask.